Fullnet, and I will be moderating this session today. Our presenter for this session is James Carpenter, who works at the European Space Agency in the Netherlands. He's a project scientist working as part of a team developing missions to the moon. James is responsible for all the scientific experiments that these missions will perform, and as well of defining the scientific requirements that must be addressed by the engineering systems. This presentation will last about 45 minutes, and after that we will dedicate about 15 minutes to your questions. In case you encounter any technical problems during the presentation, please write to my colleague Enrique in the chat. He's going with the name of Scientix EON, and he will support you through it. You can find the chat tab on the right side of the screen. And then at the end of the session, we will have some time to address your questions to our presenter. So please share your questions, comments, and suggestions in the chat. To share with everybody, please select the option Everyone in the recipient menu. So I will leave the floor to James now. Welcome everyone, and we hope you enjoy.
Great. Hello, can I just check before I start that you can see and hear me?
We can
yes,
see and
everything
hear.
works fine.
Okay, great. In which case, good morning, everybody. Thank you, everyone, for joining this morning, and thank you especially for giving me the opportunity to tell you something about the European Space Agency, about the European Space Research and Technology Centre, where I am today, and about the work that we are doing to explore the solar system with both robots and humans. So I'm joining you today from the heart of ESTEC, which is the centre of the research and technology developments that the European Space Agency does. And we are based here in the Netherlands, and we are an organisation made up of 22 different countries. So each of these countries contributes to this program because together, by bringing the different expertise, the different knowledge, the different skills, and the money from all of these different countries together, we can do things that no one country could do on their own. And so I'm going to show you today some of the very exciting things that we are doing now and that we are planning to do in the future. And so let me just show you where I am. I am in the heart of ESTEC, which is the centre in the Netherlands, and I'm in a large room. So this room was originally built to be the place where the European space shuttle, if you like, which was called Hermes, was going to be built. Now, unfortunately, that mission never came to be and that it was never built. But this room now is a place where we can demonstrate some of the things that we are building. We can show you some of what is going on, some of what we have planned, and somewhere where scientists and engineers can come to test the machines and the equipment and the things that they would like to do whilst we explore the solar system. And perhaps I should start by showing you this. So this is the International Space Station, or a model of the International Space Station. This, if you like, is one of the biggest projects that the world has ever undertaken in space. It is a place where Europe, Canada, the United States, Russia, and Japan have all come together to work together to build a huge station in space, which is somewhere where we can learn to live and work together in peace, but also a place where we can do really important scientific experiments to improve our knowledge, to increase our understanding, and to better life on Earth. Now, it's difficult for you to see, but this is an absolutely enormous space station where it is in space. And we're going to, during our tour today, I'm going to take you down there to the floor beneath me. And there you will see something called the Columbus Module. And the Columbus Module is the European Scientific Laboratory, which is on the International Space Station. And this is where our astronauts go to work to do scientific experiments while they're on the space station. So let's take a walk. So as I was saying, the European Space Agency is a an organization made up of many different countries working together. And we are working across many different areas, so looking back down at the Earth from space, doing scientific experiments, measuring the solar system with space telescopes and looking out at distant objects in the cosmos. What we're going to focus on today are exploration. So this is taking the next steps into the solar system, both with robots and with people. And so when we think of people, we have to prepare them, first of all, for the journey that they are going to take. And this requires a lot of training. And one of the ways that we train these people is to fly them in aircraft where we can simulate zero gravity. These are called parabolic aircraft. So here I have a little model of one of our parabolic aircraft. And it's a conventional aircraft, modified slightly for this. And what we do is we put the people in this aircraft, and it flies on what we call a parabola. And a parabola, the plane flies up, goes over, and comes down. And during this part of the flight, you get, just for a very short period, the sensation inside of complete zero gravity. And people will float. And in this environment, we can train our astronauts to work and to live in low gravity, and we can also perform experiments. And so what we have here is a small area simulating the inside of this aircraft, and it's somewhere where engineers and scientists can come to see how their equipment will fit into this aircraft as we prepare to go. Now, it's not just people we need to prepare for space. Anything that we would like to put in space has to be tested. One of the problems with going to space is you can't fix things very easily once they're up there, if at all. And so we have to make sure that when these things get there, and they cost us a lot of money and a lot of time and a lot of energy to prepare, we have to make sure that they work. And so these spacecraft, both robotic missions and human spacecraft, are tested. And to do that, we have very special facilities where we can simulate what it's like in space and to test them. And one of the most challenging parts of getting something into space is actually getting there in the first place. And we do that, of course, on rockets. Now, these are, behind me, you will see, I have some of the rockets that we have in Europe. So I'll start with our smallest rocket. This is our smallest rocket. It's called Vega. And Vega takes very, very small spacecraft up into to space, not far from the Earth normally. The next one we have is this. This is Soyuz. Now, Soyuz is in fact a Russian rocket. It's almost identical to the rocket that put Gagarin in space right at the beginning of the space race. It's not changed very much. It's the rocket which is still used for human missions to send humans to the International Space Station. But it is also often used to put satellites and robotic missions into space. And the reason we have it here is that through a cooperation with our partners in Russia, Soyuz is now part of the European fleet of rockets, which we launch from the European launch site, which is in French Guiana in South America. And the reason we put it in French Guiana rather than, say, in France is because when you're close to the equator, the Earth is spinning around, and you're actually moving much faster at the equator than you are up at the near the poles or at higher latitudes where Europe is, for example. And this means that when you're launching, you already get a slingshot from the spinning of the Earth, which helps you to get into space. And this is why if you look at most places where rockets are launched from, most of them are fairly close to the equator. And then this is the largest rocket in our fleet. Of course, the real ones are much larger than the ones I'm showing to you, but this is Ariane 5. So Ariane 5 is the fifth in a line of rockets that have been developed in Europe, the Ariane series. And Ariane 5 is a very large rocket. It can put very large spacecraft into space. And this has been used to launch space telescopes and other scientific missions. But it is also the most successful commercial launch vehicle. And so most, or a very large number of commercial spacecraft, telecommunications spacecraft. We use to run our mobile phones or to talk to people all over the world, things that are fundamental to making the internet work. A lot of these spacecraft have been launched on the Ariane 5 rocket. We are now starting the development of a replacement for Ariane 5, which is called Ariane 6, and that will be up and running in a few years' time. And so once you're in space, we have to operate. And what I have here is something called a proton capsule. Now, protons are essentially great big balls, and if you can see, with just a big sort of sphere. And inside this sphere, you can put a number of different things. Now, this is almost identical to the kind of spacecraft that you would put people in. So if I stand back and you can see the size of this thing, you can see it's not very big. But when astronauts go up to the space station and come back down again, this is the vehicle that actually comes and lands back on the surface of the Earth. Now, the difference with this one is that this particular version is not used for people. It is used for scientific experiments. And so inside here, you will see that it's rammed full of equipment. And so what we can do here is we can take experiments, we can fly them in space for a period of time. They come back down again and they land, and we're able to look at those and to use the measurements that they've recorded. Now, often we can put things in space and they can send signals back to us, so we don't need to get the experiments back. But for some things, it's very important to get the experiments back, particularly if you're flying things like that are alive. So, and if I can show you here, but one of the some of the experiments we will be flying cells. I'm sorry if you can't see this very well, but we're flying cells or even small insects. Sometimes you can fly little things called tardigrades, which are or other little tiny animals or small cellular organisms, or even sometimes larger animals. And these can be used to find out more about how the environment in space affects people, about how gravity affects some of the way that our bodies work, and also particularly the way that radiation in space can affect physiology and people. So that's how we get into space with these people and get back again. But then we have to ask what happens when we get there. And so earlier on I showed you the Columbus module. Columbus, now you'll see behind me, I'm standing right next to it. And we're going to step inside Columbus and take a look at what it's like inside the space station. So the inside of the space station is a very huge thing. The inside space of the space station is about the same as the inside of a jumbo jet 747 aircraft. And so as we step inside here, hope you can get some sense of where we are. So inside Columbus, we have lots and lots of these racks. So these racks will be full of scientific equipment, scientific experiments. We have glove boxes where you'd have gloves in here and you can operate inside there, looking at the different things that are in there. Sometimes things where you don't necessarily want the person to be coming into contact with the material, so particularly for biological type experiments. Now, something else you can do if you're in orbit is you can simulate lower gravity. So on Earth we have 1g, or the same gravity as we have on Earth. In low Earth orbit, as you're falling around and around and around our planet, you have the sensation of zero gravity, so you don't feel any gravity at all. But sometimes it's interesting to see what happens if you have somewhere between those two. And so here we have something called a centrifuge. And in a centrifuge, you can put experiments, and then you can spin them. And as you spin them, you actually simulate a force pushing out. The centripetal force pushes outwards, and you can simulate a certain fraction of gravity. And so that allows you to do experiments that will reduce, so you can see what happens at different levels of gravity to different kinds of things. And that can be biological processes, or it could be the physics of things like the way crystals form or the way fluids behave and other things. And so a whole range of different kinds of science take place on the space station, looking at across from fundamental physics and biology and human physiology and medical experiments. And so this is where our astronauts would come to work every day when they're on the space station. Typically, they would go to the space station for around 6 months. And typically, you would have a crew of about 6 people on the space station at any one time. Sometimes you have shorter visits, which can be around 10 days, but in general, they're much longer. You can even, there have been tourists that have gone to the space station. So you can buy a ticket to spend 10 days or so in space, and that typically would cost you around $20 million. So small change, right? So another important contribution that we have made to the space station has been to the transportation of equipment. And so for that, we built something called ATV, or the Automated Transfer Vehicle. And this is a large space truck. It carries cargo, equipment, and other things from the Earth to the space station to give them, the astronauts, food, new clothes, and new equipment. And once it's at the space station, it also fires its thrusters to push the space station up higher and higher and higher. And the reason it does that is the space station, which maybe you can see above me right here, the space station is so big, it has such a large area that even though it's in space where there is almost no air at all, it's big enough that it actually drags against the very, very thin atmosphere and slowly gets lower and lower and lower. And so every time we go up there with the ATV, we have to fire the thrusters to push the space station back up again in its orbit. Now the Automated Transfer Vehicle is finished now. That program is over, so we will not be flying any more of those. But I will show you in a few minutes what's happening next, and the way that is actually setting the road for us in ESA to go deeper into the solar system with humans. Just to show you this as well, this is so getting back again from space is very, very difficult. So you're going at very, very high speeds, and you need to slow down to get to the surface of the Earth very safely. And to do this, you have to go through the atmosphere, and the first thing you need to do is to use the atmosphere to slow you down. Now, as you do this, it generates a huge amount of heat, and this is very, very dangerous, and so we have to create special materials that can take that heat and protect the astronauts or the equipment inside. And so for that, we would use something like this. So this, what I'm standing next to, is something called the Atmospheric Reentry Demonstrator. So this was an experimental module that was flown into space and then re-entered the atmosphere. And these tiles that you see here are sort of scorched and potted. As they came through the atmosphere, they heat up to incredibly high temperatures, of 1,000 degrees or so. You'll create a layer of plasma going all the way around the module, and that takes the heat out or protects the inside from the heat. But then also it slows down the spacecraft, and so it can get to slow enough speeds that you can deploy a parachute for that final part of the descent. So now when we're thinking about what's going to happen next with people, we are now working on taking humans beyond low Earth orbit and deeper into the cosmos. And the next destination on this journey for us will be the Moon. And so we are now working with our partners in NASA to develop the multi-purpose crew vehicle, which will be the vehicle that takes humans beyond low Earth orbit and deeper into the solar system in the coming decades. And so let me just show you, this is a model of the multi-purpose crew vehicle. This part here at the front is called Orion. And Orion is a crewed capsule. So in here you'll see a very happy looking gentleman who is piloting the thing. And so this will take a number of astronauts up into space and away from the Earth. And the part at the back of this is this is called the service module, and the service module is where we have the propulsion systems, so all the fuel and the rockets and the power systems and all the systems that basically keep these people alive at the front, but also allow the vehicle to propel itself out into space. And so this is the part that's being developed here in Europe, and the first flight for this system will be in a very few years' time, and we'll go around the moon. The second flight will be shortly afterwards, and that'll be the first flight to include people. And then after that, what we're hoping to start to do is to create what we call a deep space habitat. Now, a deep space habitat is going to be not a space station, but instead you might think of it as humanity's first spaceship. So if you think about this in Star Trek terms, this is a shuttle, and the deep space habitat is the Enterprise. Now, it's not so big and exciting as the Enterprise, but it's something that will be made up of modules, a little bit like the Columbus module that you see here, with propulsion systems, and it will be able to move from different places in space near the moon. So the one place it will go is somewhere called the Earth-Moon L2 point, or the second Lagrange point. And the second Lagrange point is somewhere where the gravity of the Earth and the Moon balance out. It's a very stable place to sit in space. And from this place, you can get anywhere in the solar system, basically. So the big problem we have if we want to explore the solar system is that Earth has a lot of gravity. And getting off the Earth and into space is very, very difficult. Requires a huge amount of energy and is very costly and very dangerous. This is why we need these huge rockets that I showed you earlier to get from the Earth and into space. And this is really the thing that limits our ability to explore. If we could have a staging post somewhere which was higher in the gravity world, somewhere that was away from gravity, then we could go from Earth to this place and then go from this place to other places. And the deep space habitat is, the plan is this becomes this location. And so we would be able to go from Earth to the deep space habitat and then go from there to the surface of the moon and back in a way which is sustainable. So if you think about the extraordinary missions of the 1960s and 70s, like Apollo was an amazing program. It was way ahead of its time. But what it did is it was short missions. So it went to the surface and came back. And what we'd like to do when we think about future exploration is to think about how we can do this in a way that is sustainable in the much longer term. How can we make this work and happen so we're not going and doing a mission and then finishing, but we're going to stay, and we're going in a way that allows us to build our capabilities, to build our knowledge, and to work continuously onwards into the solar system, but in a way where the places where we go, we stay and we use them. And so, as I said, the first place that we would like to go on our journey into the solar system is the moon. And for humans, this is really the next place that you can go. Going on to Mars is a wonderful thing to do, but we have a lot to learn on the way there. We are about living and working in deep space and making that sustainable so that we don't do things in an Apollo-like way, but we do them in a way which has a much longer-term perspective. And so in preparing for the moon, we are first of all working with robotic missions. So as well as preparing some of the capabilities that we will need for humans with this multi-purpose crew vehicle with NASA, we're also working with our partners in other countries, including Russia and Roscosmos, on a lunar program. So the Russian lunar program is called Lunar. They start with a mission called Lunar 25 to remind us that the Soviet program ended in the 1970s with Lunar 26, Lunar 24. So the next mission is Lunar 25, is planned for 2019, and then that will be the start of a number of missions, and we are working with them on those. And one of the key things we would like to do with those missions is to go to the south pole of the moon and to look for potential space resources. So what we have learned in recent years is that the moon is not the place that we thought it was. At the end of the Apollo era, the moon was considered to be a dry and dead world. And experiments that were done on materials that came back from the surface of the moon showed that there was almost no water there. It was a very dry place. Now, recent missions, robotic missions to the moon, have shown us that at the polar regions, we have areas that are incredibly cold. These are some of the coldest places in the solar system. And in these places, water ice and other chemicals can become trapped in the cold. Now, water ice is potentially really, really exciting for exploration. So water, of course, is something that we need to drink, to live. But water is also made of hydrogen and oxygen. Oxygen we need to breathe, so all astronauts need it. But hydrogen and oxygen together are rocket fuel. And if you can take the oxygen from water and the hydrogen and split them up, you can bring them back together, and this creates rocket fuel. In fact, it's the same fuel that was used to power the space shuttle. And you could use then the surface of the moon as a fuel depot near Earth that we could use to get deeper into the solar system. And so something we would be trying to do with Russia in the coming program is to go to the surface, to measure this water ice, and to find out if it really is a resource that we could use for the future of exploration. We've also seen actually that water is being created at the surface of the moon all the time. So there's something called the solar wind, which is a radiation that is blown out from the sun. And the core of this solar wind is something called protons. And protons arrive at the surface of the moon. They hit the materials that are on the surface, and they create a thin layer of water. This water can then be heated by the sun. It can bounce around, and it can eventually arrive in the poles where it becomes trapped. But we also find that this water could also come from asteroids and comets that have been impacting into the surface of the moon over billions of years. And that's also really interesting because we believe, or science indicates to us, that the water that we have on Earth, the water that is in us, that is in our oceans and is in the rivers, actually probably doesn't come from Earth. It was probably delivered to the Earth early in its history by asteroids and comets and other impactors coming in from deep space. And so by going and exploring water we find on the moon, we can also find out something about our own history and the chemistry that makes us. So the moon is also a place to learn about the formation of all planets, including the Earth and our early history. And from the far side of the moon, we can do astronomy, unlike anything we can do on Earth, particularly looking at radio and looking back into the very early history of the universe. Because the Earth is very noisy in radio, and it turns out the only place in the solar system where you can't see the Earth is on the far side of the moon. And so where we're planning now to go back to the moon, as well as looking at these robotic missions with Russia, we're also developing the ways that humans and robots are going to work together in the future. So we foresee a future where we have the best of both, where there are some things that robots are really good at, and there are some things that humans are really good at. And how can we create the systems that bring those things together in the best possible way? And so we have systems like this. So this that you'll see here, this is if I stand back a bit, maybe you can see it better. This is a robot which has been developed to test some of the technologies that we will need for this. So you'll see that at the front here, we have some robotic arms, big robotic arms, and we have cameras, and these cameras and robotic arms can be used to support an astronaut who would be sort of sitting here. And so they can drive around the surface of the moon, picking things up, doing experiments and making repairs. And so we have here, for example, a model of a robotic lander of some sort, and we can do tests where we use this robot to perform functions on this lander to make repairs or deploy solar panels and other things. In fact, we've even done experiments using astronauts on the space station to control robots here. So these are experiments where an astronaut will be given some functions and things they need to do to control a robot, and we'll have a robot on the Earth, and the astronaut will control it. And this rehearses future missions where we might have an astronaut in a space station around Mars or in the deep space habitats near to the moon, where the astronaut is controlling a robot on the surface while it's working. And so when we think about the astronauts and the things that they will do, we're really thinking about the moon as the next place to go. And we're working both on our own, but also with lots of different international partners around the world to develop the ideas for how we are going to work together. So something that I think is really important about space exploration is it is something that is so big and so complicated and so extraordinary that it is something that we have to do together. And I think most countries recognize that it's something that we should really be trying to do together. And part of that is because of the scale of the challenge, but also space offers a unique opportunity to really work together and to show what's possible together. So if I take the International Space Station, for example, there is one place that I can think of in the world where all these different countries are working together on a single project in a way that is somehow independent of what is happening on the Earth, and that is the space station. And I think that our vision for the future of space exploration is that this can be something that draws us together as a species and shows us what we can do when we work in a spirit of cooperation. And so for ESA, building global cooperation and international partnerships is a fundamental part of our mission. It is a goal for the agency in doing space exploration. ESA, of course, having all these different member countries, has international cooperation at its very heart. So when we think about humans and the next steps of exploration, Moon is the next place we would go, but all of our international partners, everyone in the world, I think, all the different agencies would like Mars to be the next place that we go as a far future goal for humans. But in the meantime, Mars is somewhere that we will have to do with robots. And Mars is a fascinating place. It is the planet in the solar system that is probably most like the Earth. It is the only place in the solar system, at least in the inner solar system, where liquid water could potentially exist under some conditions. And we think from previous missions that in the past, Mars was warmer and wetter than it is today, and is somewhere that life could have emerged. And so a key thing for scientists around the world is to go to Mars, to look for the traces of life, to find out whether life ever appeared in the past, or maybe is even still present in small microbes. And that would tell us something about life. At the moment, life as we know it exists in one place, and that is the Earth. If we could find that life has emerged on Mars, the only other place that we know of where life could have existed that we can reach, then it looks like life becomes something that emerges perhaps quite often, and we are not a unique thing, an anomaly. When we look out with our space telescopes now, we see that nearly every single star has planets, and many of those planets will be in a zone near their star where liquid water could exist and could be environments where life could emerge. And so we would like to understand what are the chances that life has evolved there. And ultimately, we would like to answer the question of are we alone in the universe, or is life something which is abundant? And so these are the kinds of questions that we are trying to answer. And a first step will be to go to Mars to find out. Now, you may recall that a few weeks ago, there was an attempted landing on the surface of Mars by something called Schiaparelli. And Schiaparelli, it was a technology test. It was to test new technologies for getting to the surface of Mars. And the test was largely a success, but the final part, with the actual impact at the surface, was not what was intended, and the Schiaparelli probe landed much harder than it was supposed to, and has now formed, I think, the largest man-made crater on the surface of Mars. But this is the spare of Schiaparelli. This is the probe that was attempted to land on Mars a few weeks ago, and has exactly the same problem. If you see underneath, this is the heat shield. It's the same as or similar to the one I showed you earlier on that was tested on Earth. This is the heat shield that was supposed to take Schiaparelli to the surface of Mars and slow it down in the atmosphere. And once it reached a certain speed, then it deployed this, which is a huge parachute, which was there to slow the spacecraft down so it could land safely at the surface. Now, Schiaparelli, as I said, was a technology demonstration. It was not intended to do much at the surface, but it was carried there on a very large spacecraft. I have a model of it here. So this is the Exomars trace gas orbiter. So this is Schiaparelli sitting at on top of it there. That was released in orbit. And TGO or trace gas orbiter, is now at Mars, going around Mars, and will soon start making measurements of the atmosphere of Mars, looking for the chemical traces of life in the atmosphere, and also making images of the surface. And all of this is preparing for the next ExoMars mission, which will deploy a rover to the surface of Mars to look for chemical signs of life, and that will go in 2020. Now, we have teams all over Europe working on all of these missions. This is not something that we do here, just here in the Netherlands, but it's something which is really a Europe-wide project. And one of the places we can test is through here. You will see a laboratory where we can test robotics. So here we have a simulated Martian surface, although it can also be used as a lunar surface for some of the tests that we're doing. And you'll see over here we have the laboratory, and hopefully you can make out a couple of robotic rovers which are sitting there on the Martian surface or in the laboratory. And these rovers we can use to test technologies, to test systems, and to prepare for these Martian missions that is coming in 2020, and for the other missions that are to follow. So this is, I guess, largely what we do. We have big plans for the future. We have recently had a new program approved by the political decision makers who make the decisions on the funding for us. And so we are now working to take the missions that we have done in the past, the experience that we have on the space station, the cooperation that we have with NASA to prepare future human exploration, the cooperations that we have with Russia on taking robots to the surface of the moon, the future plans and the way that we're working with all these agencies all around the world. And we're working to bring all of that together to create a plan for Europe, but also a plan that is coordinated with space agencies and with private companies all over the world to prepare for the era of space exploration that is going to come. And I think that this next era of space exploration is going to be something quite remarkable. And the reason I think this is, if we look back at the Apollo era and what happened in Apollo, Apollo was an extraordinary event that everybody in the world participated in through. I think everyone felt that they were somehow a part of this, it really brought the world together for a moment. And that was possible through a new technology that was television. And if we look forward to space exploration over the next 10 years, 20 years, 30 years, and we look at the technologies that we have now and the technologies that we can't even conceive of yet, that will allow people to participate in this, be it through social media, through virtual reality, through concepts that we don't even know about yet. I think that the next era of space exploration will be something that all of us participate in and all of us are able to contribute to. And I think that's something that's very, very exciting. And so thinking about how we can participate in this both as consumers, if you like, as parts of the population, I think there are also very real possibilities for participating in this as one of the scientists, the engineers, or the various other people that will make this happen. The space industry is something that is growing. It is exciting. There are many opportunities, not just in exploration, but in navigation, in telecommunications, in science, in many areas. And there is really a need for people with the skills and the ability to make this happen. And so what we need in the industry are people who have studied science, people who have studied mathematics or engineering and technology, people who can come up with new ideas, people who can build things. But even beyond that, we need people, we need lawyers, we need people who are working in international relations. We need people to run the machinery of the agencies and of the industries and of the companies that are going to make this happen. And so I think that this is a really exciting time to be a student or to be at school, because the people that are going to make this happen, the first people to travel to the surface of the moon in many, many years, the first people to do so many things, the people that are going to make exploration happen and are going to really participate in exploration are probably in school now and are probably in their early time at university now. And so I was excited when I was at school, when I discovered that space and going to space with robots and creating spacecraft and working in this field was possible, and that excited me tremendously. I think that now is a much more exciting time. I think there are more opportunities, and there's a really exciting future coming, and so the decisions that you make now will inform, will allow you to participate in this and to become a part of this global adventure, an adventure for humanity. And I hope that many of you will choose to join us in this adventure. So with that, I think I probably will close my presentation. I know I've seen while I've been talking that there have been lots of questions, and I would be delighted to take questions and to do my very best to answer where I can. Thank you.
Thank you, James. That was a great presentation. Indeed, we have many, many, many questions. I think I got them all written down. I think we should start by some of the questions by the youngest students here. So I think we have 3 different teachers with a bunch of students, and they've been asking a lot of questions. So I'll just go ahead and I'll pick some. So Marina Moya, she has a student called Beza that asks, are there girls engineers and that work with you?
Absolutely. Absolutely. I think there is, engineering is not something which is gender specific. My boss is one of the finest engineers I've ever met, and she is a woman. I think that actually we see more and more women coming into to the space field and into the industry. And there is no reason why there is any difference in terms of men or women in terms of your ability to be a good engineer or a good scientist. So I would absolutely encourage any girls or young women who think that this is something that they're interested in and that they would like to pursue to do so, because I think there are great opportunities for women, and there are a lot of fantastic engineers working with me here.
That is actually great to know. From another teacher, this one's called Alina Steyu. She's got also a lot of students, and let me see some of the questions. Gabriel asks, have you ever been to the moon? And Minea asks, when will humans arrive to Saturn?
Oh, good question. So I have not been to the moon. In fact, nobody has been to the moon for quite a long time. So it's many, many years since anybody went to the moon. So that was happened during the Apollo missions of the 1970s. Humans went to the moon. This was very expensive, and the priorities in the United States changed. And this Apollo was an American program, and so that program was stopped, and nobody has been back to the moon since. And so what we're starting to see now is a re-emergence of interest in human space exploration. The focus for a long time was on developing space stations in low Earth orbit, so all the money and the expertise went into building things like this, which you see behind me, the Columbus module and the International Space Station. The space station will come to the end of its time during the 2020s. Then we'll probably continue having operations in near-Earth space with other kinds of space stations, perhaps commercial space stations or from other countries. But now the focus goes back to taking humans beyond, and so we are currently expecting the next human missions to the moon to happen around 2030.
Okay. Now we have some questions related to.
Oh,
space
sorry.
missions.
Sorry. There was one question on Saturn.
Yes. Yes. There was
So
one
sorry.
on Saturn.
I think one day we'll see humans going to Saturn. Humans will never stand on Saturn because Saturn doesn't have a solid surface to stand on. It's made of gas. But I think we'll see humans going to the Saturn system, but I probably won't happen in my lifetime. So getting out there is very, very difficult. It takes a very, very long time. And at the moment, the huge challenge for us is to think about how we can get a human to Mars. If we can do that, is something that I think could happen in my lifetime, potentially in my career, probably not. But humans to Saturn, that's really a much further future.
Okay, then we have, moving on, we have Yvonne who asks, how long is a mission in space? And Edward, how many years an astronaut has to train to go into space?
Okay, so a mission to space can take a very, very different periods of time. So human missions going to the space station typically last for 6 months. They can last for 10 days. The robotic missions that we fly can last for several years, so they can last for a very long time. If we want to send humans to Mars, then we are looking at missions that will take probably 6 months to get there, probably a year or so at the surface of Mars, or maybe more, and then another 6 months to come back. So these deep space missions for humans are going to take several years. Oh, I'm sorry.
Sorry, can you hear me now?
Yes, I hear you now, yes.
Okay, sorry. I was saying that now that we are on the topic of Mars, Mary is asking if you can grow vegetables on Mars.
Well, this is something that we don't know. Because to make plants grow, we need all the different nutrients, but there's also all sorts of microbiology that you need to make Mars, to make soil fertile and to grow plants. So the kind of things that perhaps we will find out from missions like Exomars and the other robotic missions is what really is possible at the surface of Mars. So we think it should be possible with a little bit of help. Then also the Martian. The astronaut in the Martian has a very particular way of his own of making the soil fertile to grow potatoes. So it may be possible to do, but today we don't really know for sure.
Okay, so I think that's all from like the younger students' questions. I'll go back to some questions that were asked at the beginning. One by Nias Chaudhry, sorry for my pronunciation. She asks, what are the sources of electrical energy in space to make those machines active, and how do engineers maintain a smooth flow of such energy there? I think this was asked while inside the Columbus modules.
Okay, so in space there are two ways that you can get your electricity. The first, and the one that is generally used, is to use solar power. Perhaps if I come over here, you can see an example. So most satellites will use these. So behind me, you'll see the multi-purpose crew vehicle, and you'll see solar panels extending out from the side of it. So these solar panels capture the light from the sun, and they convert them into electricity. And then that electricity would be used to power the spacecraft, but also to fill batteries. And those batteries would be used in periods where you can't see the sun. So that's probably the main way that you would do this on in space. Now, sometimes solar power isn't available. So if you're in somewhere which is dark for a long time, or if you're going out deep into the solar system, so for example, out to Saturn, for example, then solar power doesn't work. So then you need to use nuclear. And that's like a nuclear reactor, the kind of thing that you would have on Earth. Rather, you take a piece of radioactive material, and that radioactive material will be warm. And you use the heat that this radioactive material gives off to turn that into electricity. So that is good because it means you don't need sunlight, but it is quite heavy. You don't generate a great deal of electricity. It's not very efficient. But it's really the only other way that we have today of providing power in space.
Okay, we have another question by Jose Maria, and he asks, what is the approximate mass of the entire space station? We need the data to make some small predictions, I guess, with the students.
Okay, I'm afraid I don't have that information in my head. I suspect Google will tell you, but if you need me to follow up on that and provide that number for you, then I can do that very easily.
Okay, then we'll give him the details. There's another very interesting question that goes like, what type of communication system is used in space, and how far can this communicate?
Okay, so the main way that we would communicate in space is using radio communications in different radio frequencies. And so typically you would have a ground station on the Earth, so a big dish on the Earth that will be receiving the signals. Or even actually your phone also receives signals from space with your GPS. So if you have a GPS on your smartphone, this is receiving signals that are coming from satellites that are in space. And so this is normally the way that we would communicate. One of the problems with this is that there are only so many radio frequencies. So if you have too many satellites broadcasting at the same time, and you also have all the communications on Earth, all operating in different radio frequencies, eventually you just run out of radio frequencies. You can't do any more. So that's one problem. The second problem is that you are limited in how much data you can transmit from a spacecraft to the ground in radio. So if you want more data, then you need more power, which means you need bigger solar panels and bigger batteries. But you also need bigger antennae, so different dishes, bigger systems. And these are all bigger and heavier and more difficult to get into space. So another way that you can do it, and this is much newer, is to use laser beams. And so these aren't being used as a normal way of communicating at the moment, but in the future we will see laser beams targeted from spacecraft to other spacecraft and to stations on the ground. And these laser beams, because they're very, very focused, very narrow, they don't interfere with each other, and you can get a huge amount of data transmitted through the laser light. So this is something that will become more and more important in the future.
Okay, thank you for the answer. I have a couple more questions, the two last ones that have just popped up in the chat. The first one is, what makes the Earth so special for living? Is it just the position in space and the distance from the sun, or are there some other things?
Okay, so I think there are lots. And so the first is its position in space, meaning that the temperature, position relative to the sun, is such that the temperature that we have on Earth is just in that very narrow band where liquid water can exist. And liquid water is fundamental to life. So that's the first thing. It's also large enough that it has kept its atmosphere, which also allows us to keep the water on the surface of the Earth. So the Moon, for example, or Mercury have no atmosphere. And one of the reasons for that is that they have much lower gravity, and so the atmosphere has escaped. We have a magnetic field, so the inside of the Earth is molten and it's rotating, and this generates electric currents, and those electric currents create a magnetic field, and that magnetic field is a force field that protects the planet from the material that's being thrown out by the sun, and that has also meant that life on Earth is possible. That force field also protects us from the radiation that comes from deep space, which has also allowed life to exist. I see that my battery is getting low on my phone, so it's possible I might lose you in a minute or two. In which case I will run over and get my laptop. Maybe I'll head over there now, just in case. So those are all important things, but also the chemistry that exists on Earth that enables life. So the complex organic molecules, things like amino acids and proteins. We think that these chemicals have been delivered to the Earth by, we don't know exactly where they come from, but they may have come from space. And so the unique history of the Earth in terms of the impact and the way that chemistry has been delivered to our planet have also made it possible for life to exist. So it's a very complex thing. Yeah. So just to check with you, can you see me on this my computer now?
Hi, we can see. Yeah, we can see you.
Okay, so I'm going to suggest that I just quickly switch for the last few minutes to my laptop, just to make sure that my battery doesn't give up on us.
Oh, well, okay.
Is that possible?
Yeah, but we were gonna wrap up in a couple of minutes or so it's okay.
Yes, I'll stick with this.
Okay, so I think actually that should be the last question, because I don't think we're gonna have time for more.
Okay.
Okay, so thank you very much, James, for this session. We're going to wrap up here. Thank you, everyone, for participating, and we hope to see you online. And the recordings of this webinar, they will be available in the following days. So please follow the Career Hub of the project to access these resources later on this week. Thanks again, everyone. We apologize because we know we haven't been able to answer all of the questions, but we did our best. So thank you, everyone, again, and have a nice day. Thank you, James.